Hello, everyone. Today, I will present our work, durable top K instant stamp temporal records with user-specified scoring functions. Before I dive into the problem, let's first see a few headline statements from the media in our daily life. For example, in late January 2019, an extreme cold wave hit the Midwestern United States and brought the coldest temperatures in the past 20 years to most locations in the affected region, including some all-time record lows. Similarly, in another example in sports domain, on January 22nd, 2006, Kobe Bryant scored 81 points against Toronto Raptors. At that time, this record was the top one scoring performance in the past 45 years of NBA history. And since then, this scoring record has yet to be broken. This type of statement, using the combination of ranking and time duration, is widely used in the media or marketing to emphasize the impressiveness of certain events, because naturally, people are attracted by those things that stood the test of time. Motivated by this, we consider a new type of query called tau durable top K queries that can return such interesting or unusual records from the instant stamped temporal data. Here, tau is the time duration, showing that a record would rank on top in comparison to all other records during this time period. So if we take a closer look on the Kobe Bryant statements, for example, here we plot the all NBA player scoring performance in NBA history, we can clearly see that Kobe Bryant's 81-point game ranked top one in the 45 years window in the past. Another example would be another player, Devin Booker, his 70-point game ranked top one in the 11-year window in the past. So a tau durable top query would ask for such dominant records with durability window length greater or equal than tau. So the example we show here is just 1D data, but the ranking function or the scoring function would be generalized to higher dimensional data, where users can plug in their ranking preferences into the scoring function. So here is the overview of my talk. So we will start with this problem formulation, and then I will highlight the novelty and contribution of our proposed solution. And in the end, I will show some experiments to demonstrate the efficiency of our solution in practice. So formally, let's define a temporal dataset P consists of n records with multiple attributes. Let pi of k denotes the top k records with regarding to a preference function f on durability window w. We say a record P is tau durable if P belongs to the top K set on a tau length window ending at its timestamp. It's worth mentioning that the window positioning does not have to be only in this way. So it's kind of like we look back into time, but it can also look forward, something like this, from PT to PT plus tau. So how to define the window positioning depends on the application scenarios and how we interpret results. But in this paper, we only assume that the relative positioning is done consistently across all records. So finally, given the scoring function f across interval I, a durable top K preference top K query will return a set of records and arriving during the I with durability at least tau. So users can try different combination of these query parameters at query time to find more insights from the temporal data. So now let's take a look at our proposed solution. So in order to check whether a record is tau durable, we need to run the top K queries on a subset of the data. And a straightforward baseline solution is to run the top K queries over consecutive moving windows, much like the sliding window technique for monitoring the top K queries on data streams. So though the sliding window is already well studied and we have some very efficient and elegant algorithms, it's not suitable for our setting since the data we have is not online data streams. We have all the historical data available. And so apparently the baseline solution would ask too many unnecessary top K queries. So in this work, we mainly ask the following two questions. The first, we ask how to reduce the number of topic queries. So we provide a set of efficient algorithms to answer this question. And then next, we further answer a more fundamental questions of the query itself and of our algorithms. So how many topic queries do we really need? So the first question, the key idea to reduce the number of topic queries is pruning. An important observation is that existing durable answers can help to prune non-durable records. And as more answers are found, the stronger the pruning power. So there are multiple ways to do the pruning. We introduce two types of them. First, time prioritized type pruning. We use the following toy example to illustrate the idea. Let's say we consider top one durability. So we sequentially process the records in order of their arriving time. So for example, let's start with P1. We ask a topic query shown as the red arrow. And it turns out P1 is not durable because since P3 rank at the top one during this time period. Traditionally, we would next go to P2 and ask another topic query to check its durability. But actually, we do not need to do that. Since from the first topic queries, we already know that between time T1, T3, P3 is the top one. In other words, no other records during this time period will be top one durable. So we can safely skip the entire time domain, the entire time interval here, as we're taking a hop in time. So the similar procedure can be generalized to top K case. So we can save a lot of unnecessary topic queries by doing the time prioritized pruning. Another type of pruning is score prioritized pruning. So in this case, we sequentially process the records by their score in descending order. So by doing this, it automatically enables the blocking mechanism for pruning. Because intuitively, those high score records themselves can be viewed as landmarks and they block nearby records to be in the top K. So let's say we use this black intervals to show that we call what we call blocking intervals. For example, P4 has a high score. So any record that arrive after P4 will be blocked by P4. Thus cannot be top one durable. So any record will create such blocking intervals. And with this idea, the query procedure is the following. We process the records based on their scores from high to low. For example, we start with P4, we ask a topic query, and we add in a blocking interval. Then for P3, we can easily find that P3 is already covered by one blocking interval, which induced by P4, which means that it cannot be a durable top one record. So we can save a topic query here and just add a blocking interval. Well, similarly for P1 and P2, and finally, we come to P5, it's not blocked by any other record, so we need to ask a topic query to check and also adding the blocking interval. So overall, due to the blocking intervals, we only need to ask 2 topic queries instead of 5. So take analogy here. So for the time priority pruning, we take a hop in time, but here we take a hop in the score domain. So this is the 2 algorithms that we have to reduce the number of topic queries. So next, let's answer the harder question. Now, how many topic queries do we really need? Now, in our paper, we present the following 2 theorems to answer this question. First, given the query parameters k, the function f, the tau and I, both algorithm performs at most the big O of S plus Ki over tau preference topic queries, where S is answer size. A quick reminder that Ki, tau are query parameters given at query time, and I is a query interval, and tau is a durability window length. And we further show that under the random permutation model, given the query parameters, the expected answer set S equals Ki over tau plus 1. So a random permutation model here is a very general but also practical models, where the score of the records can be arbitrarily chosen, and we only assume that their arriving order is random. So if we combine these 2 theorems together, we can show that the number of topic queries we need is expected to be the answer size, or which equivalently the ki over tau. Or in other words, the complexity of our proposed algorithm is essentially only linear to the answer side. It's worth mentioning that our conclusion is mostly to view the top K query as a black box model. So it can work with a broad class of ranking functions and top K algorithms. So be it linear or non-linear, monotone or non-monotone, as long as there exists a well-defined building block to efficiently answer regular top K queries, we show that invocation to that black box are always bounded by answer size using our proposed algorithm. Lastly, let's see some experiments. We mainly focus on the query efficiency comparison among different solutions. So here in the first figure, we vary the query selectivity on the x-axis and show the query time in milliseconds on the y-axis. So as can be seen, our proposed pruning-based solution is out-persistive, while being more efficient as the query is more selective. So it can be up to an order of magnitude faster than the baseline solution, which is based on the moving window technique, sliding window technique. This confirms our conclusion that the complexity of these two algorithms are essentially linear to the answer side. And next, we show that our algorithms scale well in terms of the data dimensionality. So at the x-axis, we vary the data dimensions from 2 up to 37. And compared to the baseline, our solution is consistently at least 10 times faster than the baseline. And finally, we show that our algorithm also scales well on data size. So we vary the data set from 1 million records to 50 million records. Well, we can see that it still provides up to 2 orders of magnitude, two orders of magnitude query efficiency improvement. And another nice property we can see here is the running time of our solutions mostly stays the same across varying data size. Again, confirming that the complexity of our proposed algorithm is essentially only linear to the answer size, well, regardless of the data dimensionality or the data size. Well, lastly, a brief summary of the talk. So we considered how durable top K queries on instant stamp temporal data with general preference ranking functions. And our solutions are efficient with provable complexity guarantee that is only linear to the answer size. In practice, it can be up to 100 times faster than standard techniques. Thank you. That's my talk, and I'm happy to take questions right now.